So, here's something worth thinking about as you settle in tonight. Right now, somewhere on this planet, there are people trying to build a small star. Not metaphorically, not poetically. They are literally trying to recreate the process that powers the sun, that powers every star you've ever seen in the night sky, and they're trying to do it in a building, in a machine, on Earth. And they've been trying, in one form or another, for about 70 years, which is either a testament to human stubbornness or a sign that this is genuinely one of the hardest things our species has ever attempted. Probably both. Nuclear fusion. You've heard the term. You might have a rough sense of what it means. You might also have heard the old joke. Fusion is the energy source of the future, and it always will be. People have been saying that since the 1950s. And yet, here we are, still working on it, still pouring billions into it, and in the last few years, something has shifted. There have been breakthroughs that would have seemed impossible a decade ago. But we'll get to all of that. Tonight, we're going to take this whole thing apart, slowly, from the very beginning. No rush. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here, and honestly, some of them are the kind of thing that's nice to fall asleep thinking about. Let's start with the most basic question. What is fusion? And I mean really, what's actually happening? You know that everything around you is made of atoms. The pillow under your head, the air in the room, you yourself, all atoms. And every atom has a nucleus at its center, this incredibly tiny, incredibly dense knot of particles. Protons and neutrons packed together. Now, under normal conditions, atomic nuclei want nothing to do with each other. They're all positively charged. The protons carry positive electric charge, and positive charges repel each other. You know this if you've ever tried to push two magnets together the wrong way. They fight you. They slide apart. Nuclei are like that, except the repulsive force is electromagnetic, and it's ferocious. The closer two nuclei get, the harder they push each other away. But here's the thing. If you can somehow force two light nuclei close enough together, and we're talking absurdly close, like within a femtometer, a millionth of a billionth of a millimeter, something remarkable happens. A different force takes over. The strong nuclear force. It's called that because, well, it's strong. It's the strongest force in the known universe, actually. But it only works at incredibly short range. It's like a handshake that only works if you're already touching. Once two nuclei get within that tiny distance, the strong force grabs them and fuses them together into a new, heavier nucleus. And when that happens, a little bit of mass, a tiny, tiny amount of matter, gets converted directly into energy. And that's fusion. That's the whole idea. You take two small atomic nuclei, you smash them together hard enough to overcome their electrical repulsion, and they merge into something new, releasing energy in the process. The energy comes from Einstein's famous equation, E equals mc squared. The m there is the mass that disappears. The new nucleus weighs slightly less than the two original nuclei combined, and the c is the speed of light. The speed of light is an enormous number, and you're squaring it, so even a tiny amount of mass converts into a staggering amount of energy. We're talking about a few milligrams of fuel producing the energy equivalent of tons of conventional fuel. It's almost absurd how much energy is locked up in there. Now, the sun does this. The sun has been doing this for about 4.5 billion years, and it's going to keep doing it for another 5 billion or so. Every second, the sun fuses roughly 600 million tons of hydrogen into helium. 600 million tons per second. and about 4 million tons of that mass simply vanishes, converted into pure energy, into the light and heat that crosses 93 million miles of space and lands on your face on a summer afternoon. That warmth you feel? That started as hydrogen atoms being crushed together in the core of the sun, where the temperature is about 15 million degrees Celsius and the pressure is about 250 billion times the atmospheric pressure here on Earth's surface. And that pressure part is really important because the sun has a massive advantage that we don't have. It's enormous. It has a colossal gravitational field that squeezes its core relentlessly. All that weight, all that mass pressing inward, creates the conditions where hydrogen nuclei are forced close enough together, often enough that fusion happens at a steady rate. The sun doesn't need a fancy machine. It just uses its own gravity. It's essentially a self-sustaining fusion reactor held together by its own weight. We don't have that luxury. On Earth, we can't just pile up enough hydrogen to create a star-sized gravitational field. Well, we could in theory, but then we'd have a star, which sort of defeats the purpose of building a power plant. So we have to find another way to get those nuclei close enough together. And that means we need to make things very, very hot. Unimaginably hot. We're talking about temperatures of 100 million degrees Celsius or more. That's roughly 6 to 7 times hotter than the center of the sun. Think about that for a second. We need to create temperatures hotter than the core of the sun, here on Earth, inside a machine. The reason we need it even hotter than the sun is precisely because we can't match the sun's pressure. We're compensating for lower pressure with higher temperature, giving those nuclei more kinetic energy, more speed, so they slam into each other hard enough to overcome the electromagnetic repulsion even without a star's worth of gravity squeezing them together. At those temperatures, matter enters a state called plasma. You know about solids, liquids, and gases, right? Plasma is sometimes called the fourth state of matter. Heat a gas enough and the electrons get ripped away from their atoms entirely. You're left with this roiling soup of free electrons and bare nuclei, all zipping around at tremendous speeds. Plasma is actually the most common state of matter in the visible universe. Stars are made of it. The solar wind is plasma. Those gorgeous nebulae in telescope photos are plasma. But here on Earth, we don't encounter it much in daily life. Lightning is plasma. The glowing gas inside a neon sign is a mild plasma. The inside of a fluorescent light bulb, that's plasma too. But the plasma you need for fusion is in a completely different league. It's 100 million degrees. Nothing can touch it. No material can contain it. Any wall, any surface, any substance you can name would vaporize instantly if it came into contact with plasma that hot. So how do you hold something that hot? How do you contain a tiny piece of star stuff without a container? That's one of the fundamental problems of fusion, and people have been wrestling with it since the very beginning. But before we get into the engineering of containment, let's rewind a bit, because the story of how humans even figured out that fusion was a thing, that the sun was powered by nuclear reactions rather than, say, burning coal or slowly contracting under gravity. That story is wonderful, and it starts earlier than you might think. In the 19th century, people had a serious problem. They couldn't figure out how old the sun was, or more precisely, they couldn't figure out how it kept shining. If the sun were made of coal, the best fuel anyone knew, and you lit it on fire, it would burn out in a few thousand years. That obviously didn't match the geological evidence, which even by the mid-1800s was suggesting that the Earth, and therefore the sun, was millions of years old at minimum. Lord Kelvin, one of the towering figures of Victorian physics, proposed that the sun was slowly shrinking, converting gravitational potential energy into heat. That was clever, and it bought you maybe 20 or 30 million years. But even that wasn't enough. Geologists and biologists, particularly Darwin, needed far more time than that for their theories to work. There was a genuine scientific standoff. The physicists said the sun couldn't be that old. The geologists and biologists said the Earth clearly was. Somebody was wrong. The answer, of course, was that the physicists were wrong, but not because their physics was bad. They were working with incomplete physics. They didn't know about nuclear reactions yet. Nobody did. The discovery of radioactivity in the 1890s by Henri Becquerel, and then the work of Marie and Pierre Curie, started to crack things open. Here was a process that released energy from within the atom itself, energy that had nothing to do with chemical burning or gravitational contraction. But it took decades more before anyone connected this to the sun. The key figure here is Arthur Eddington, a brilliant British astrophysicist. In the 1920s, Eddington was already famous for confirming Einstein's general theory of relativity during a solar eclipse in 1919. But his work on stellar structure was equally groundbreaking. Eddington understood that the interior of a star must be extraordinarily hot and dense, and he began to suspect that subatomic processes, what we now call nuclear reactions, were the source of stellar energy. In 1920, he noted something crucial. Francis Aston, working at Cambridge with his newly invented mass spectrograph, had measured the mass of a helium atom and found that it was slightly less than 4 times the mass of a hydrogen atom. 4 hydrogen nuclei somehow weighed more than 1 helium nucleus. Where did that missing mass go? Eddington made the leap. He suggested that if 4 hydrogen atoms could somehow combine to form 1 helium atom, the missing mass would be converted into energy via Einstein's equation. And he calculated that this process could power the sun for billions of years. Billions. That solved the standoff. He wrote, and I love this quote, "If indeed the subatomic energy in the stars is being freely used to maintain their great furnaces, it seems to bring a little nearer to fulfillment our dream of controlling this latent power for the well-being of the human race." That was 1920. He was already thinking about fusion power on Earth 100 years ago. But knowing that fusion powered the stars and understanding exactly how it happened were 2 very different things. The detailed mechanism, the specific chain of reactions that converts hydrogen to helium inside the sun, wasn't worked out until the late 1930s, and it took 2 people working more or less independently to crack it. One was Hans Bethe, a German-born physicist who had fled Nazi Germany and settled in the United States at Cornell University. The other was Carl Friedrich von Weizsäcker, who was still in Germany. Bethe's work was particularly remarkable. He essentially worked out the carbon-nitrogen-oxygen cycle, one of the 2 main fusion pathways in stars, during a conference in Washington, D.C. in 1938, and then on the train ride home. On a train. He refined it over the following months and published it in 1939. He'd later win the Nobel Prize for this work in 1967. The other main pathway, the proton-proton chain, is actually the dominant one in our sun. It's simpler, conceptually. 2 protons, hydrogen nuclei, collide, and one of them undergoes a transformation, turning into a neutron via the weak nuclear force, releasing a positron and a neutrino. What you're left with is a deuterium nucleus, 1 proton and 1 neutron bound together. Deuterium is just a heavier version of hydrogen, sometimes called heavy hydrogen. Then that deuterium nucleus collides with another proton to form helium-3, a light isotope of helium. And finally, two helium-3 nuclei collide to form regular helium-4, spitting out 2 protons in the process. The net result: 4 protons go in, 1 helium-4 nucleus comes out, along with some positrons, neutrinos, and a whole lot of energy. Now here's a detail that might surprise you. This process is incredibly slow. Any individual proton in the sun's core will bounce around for an average of about 1 billion years before it successfully fuses with another proton. 1 billion years. The sun gets away with this because it has an unfathomable number of protons. The sheer volume compensates for the low probability of any single reaction. But this tells you something important about the challenge of doing fusion on Earth. We can't wait 1 billion years. We can't use 1 trillion tons of hydrogen. We need to make fusion happen fast, in a small volume, with a manageable amount of fuel. And that means we need to be much, much cleverer about which specific fusion reaction we use. This is where deuterium and tritium enter the story. And honestly, this is where the whole modern quest for fusion energy really begins. Because it turns out that not all fusion reactions are equally easy to achieve. The proton-proton chain that powers the sun is actually one of the hardest to replicate, because it relies on the weak nuclear force, which is, well, weak, rare, slow. But there's a different reaction, one involving 2 heavier isotopes of hydrogen that's far more accessible. Deuterium, 1 proton, 1 neutron, fusing with tritium, 1 proton, 2 neutrons. When a deuterium nucleus and a tritium nucleus collide and fuse, they produce a helium-4 nucleus, a free neutron, and about 17.6 million electron volts of energy. And critically, this reaction has the highest cross-section, the highest probability of occurring, at temperatures that are, while still extreme, within the realm of what we might actually achieve in a laboratory. We're talking about around 100 to 200 million degrees. Still staggering, but not impossible. And deuterium is abundant, spectacularly abundant. About 1 in every 6,000 hydrogen atoms in ordinary water is deuterium. The oceans are full of it. A single gallon of seawater contains enough deuterium to produce the energy equivalent of about 300 gallons of gasoline, if you could fuse it all. Tritium is trickier. It's radioactive, with a half-life of about 12 years, so it doesn't occur naturally in useful quantities. But it can be bred from lithium, which is another story we'll get into later. The point is, the fuel for fusion is, in principle, nearly limitless, and the primary byproduct is helium, an inert, harmless gas. No carbon dioxide, no long-lived radioactive waste like you get from fission reactors, no risk of meltdown, because if anything goes wrong with a fusion reaction, it simply stops. The plasma cools, the reaction fizzles out. You can't have a runaway fusion reaction the way you can have a runaway fission reaction. So the promise is extraordinary. Essentially unlimited clean energy from seawater. It sounds like science fiction, and in the late 1940s and early 1950s, when physicists first started seriously thinking about building fusion reactors, some of them genuinely believed they'd have it figured out within 20 years. They were brilliant people, and they understood the physics beautifully. What they underestimated, what almost everyone underestimated, was the sheer brutal difficulty of the engineering. Because understanding that you need to heat plasma to 100 million degrees is one thing. Actually doing it and keeping it stable and confining it long enough for enough reactions to occur to produce net energy, that turned out to be a problem of almost incomprehensible complexity. And the first people to seriously tackle that problem were working in secret in 3 different countries simultaneously. In the early years of the Cold War, each group unaware that the others even existed. The Americans, the Soviets, and the British, all 3 launched classified fusion research programs within a few years of each other, and for nearly a decade, none of them shared a word about what they were doing. Let's start with the British, because their story has a kind of scrappy charm to it. In the late 1940s, a physicist named George Paget Thomson, and yes, that's the son of J.J. Thomson, the man who discovered the electron, George Thomson filed a patent for a fusion reactor. Think about that. The physics of fusion had barely been worked out. Nobody had come close to building one, and here's Thomson filing paperwork with the British government, essentially saying, "I have an idea for how to make this work." His concept was relatively simple. You'd create a powerful electrical discharge inside a tube of gas, and the current flowing through the gas would generate a magnetic field that would pinch the plasma inward, compressing and heating it. This idea, using the plasma's own magnetic field to squeeze itself, became known as the pinch effect. And it's a beautiful concept, really. Imagine you've got a column of electrically conducting gas, and you run a massive current through it. That current creates a magnetic field that wraps around the column like a tightening fist, and the plasma gets squeezed inward, getting denser and hotter. In theory, if you squeeze hard enough and fast enough, you could reach fusion conditions. The British took this idea and ran with it. By the early 1950s, they had a series of experimental devices at Harwell, their atomic research establishment, and the work eventually moved to a facility called the Atomic Energy Research Establishment at Aldermaston, and then to Harwell proper. The most famous of these early British machines was called Zeta, the Zero Energy Thermonuclear Assembly. Now, Zeta wasn't built until 1957, but the groundwork was being laid throughout the early 50s, and the British were genuinely excited. They thought the pinch approach might be the fast track to fusion power. Meanwhile, across the Atlantic, the Americans were pursuing their own ideas. And here's where we meet one of the most fascinating figures in the whole fusion story, a man named Lyman Spitzer. Spitzer was an astrophysicist at Princeton, and in 1951, he had what you might call a eureka moment, though it came from a somewhat unlikely source. He'd read a newspaper report, and this is a wonderful detail, about an Argentine scientist named Ronald Richter, who claimed to have achieved controlled fusion. Richter was working under the patronage of Juan Perón, and he announced to the world that Argentina had cracked fusion. It was front-page news, and it turned out to be completely false. Richter's claims were bogus, his experiments were flawed, and the whole thing was eventually debunked and became something of an embarrassment. But here's the thing, that false claim lit a fire under Lyman Spitzer. He started thinking seriously about how you actually would confine a plasma magnetically, and within weeks, he'd sketched out an entirely new concept. Spitzer's idea was different from the British pinch approach. Instead of using the plasma's own current to squeeze itself, he proposed building an external magnetic bottle, a carefully shaped magnetic field that would hold the plasma in place from the outside. And the shape he came up with was extraordinary. Imagine taking a donut, a torus, and then twisting it into a figure 8. That's essentially what Spitzer proposed. He called it the stellarator, from the Latin word for star, because the goal was to recreate stellar conditions. The reason for that twist is subtle and important, and it gets at one of the deep problems of magnetic confinement that those early researchers were just beginning to understand. See, if you just make a simple donut-shaped magnetic field, a plain torus, you run into a problem. The magnetic field on the inside of the donut, closer to the center of the ring, is stronger than the field on the outside. That difference in field strength causes the charged particles in your plasma to drift. They don't just spiral neatly along the field lines, they gradually drift sideways, and eventually they hit the wall of your container, and the plasma falls apart. It's like trying to hold water in a bowl that's tilted. It just slides out. Spitzer realized that if you twisted the shape of the torus, you could make the particles spend equal time on the inside and the outside, so those drifts would cancel out over a full orbit. It's a genuinely clever piece of geometric thinking, and it set the stage for an entire family of fusion devices that are still being refined today, 70 years later. Spitzer got funding from the Atomic Energy Commission, classified funding, of course, and set up a laboratory at Princeton that would eventually become the Princeton Plasma Physics Laboratory, one of the most important fusion research centers in the world. The project was codenamed Project Matterhorn, supposedly because Spitzer loved skiing and had recently been to the Alps, which is a delightful reason to name a top-secret nuclear research program, if you think about it. Now, over in the Soviet Union, the story takes yet another shape, and the key figures here are two physicists whose names you'll hear over and over in the fusion story: Andrei Sakharov and Igor Tamm. Sakharov would later become world famous as a dissident and human rights advocate, and he'd win the Nobel Peace Prize in 1975. But in the early 1950s, he was a young physicist working on the Soviet hydrogen bomb program, and he and Tamm proposed their own approach to magnetic confinement. Their idea was, in some ways, simpler than Spitzer's stellarator. Instead of twisting the whole shape of the container, they proposed using a plain donut-shaped chamber, a torus, but solving the particle drift problem by running a current through the plasma itself. That current would create an additional magnetic field component that would twist the field lines, achieving a similar effect to Spitzer's physical twist, but through electromagnetic means rather than geometric ones. The field lines in their device would spiral around the torus in a helical pattern, and particles following those spiraling lines would naturally spend time on both the inside and outside of the donut, canceling out those problematic drifts. They called this device the tokamak, a Russian acronym that translates roughly to toroidal chamber with magnetic coils. And here's what I want you to appreciate about this moment. You've got three groups of brilliant people working independently, all converging on the same fundamental insight, that magnetic fields are the key to confining plasma, and that the geometry of those fields matters enormously. But they each arrived at different solutions. The British said, "Let the plasma pinch itself." Spitzer said, "Twist the container." Sakharov and Tamm said, "Twist the field with a plasma current." Three different answers to the same impossible question, and the competition between these approaches. Which one would work best? Which one could actually lead to a power plant? That competition would define fusion research for decades. Now, let's talk about what happened when these groups actually started running experiments, because this is where reality delivered its first harsh lessons. The British pinch experiments, which had seemed so promising on paper, ran into trouble almost immediately. The problem was something called instabilities. When you try to pinch a column of plasma with a magnetic field, the plasma doesn't just sit there cooperatively getting squeezed. It writhes, it kinks, it develops bulges and twists, like trying to squeeze a wet bar of soap. It squirts out sideways. These instabilities have wonderful descriptive names. There's the sausage instability, where the plasma column develops periodic bulges that look like a string of sausages. And there's the kink instability, where the whole column bends and writhes like a snake. Both of these can happen in microseconds, and both of them destroy your confinement almost instantly. The British discovered this the hard way. Their early pinch machines would fire, the plasma would light up, they'd see a burst of neutrons, which is what you'd expect from fusion reactions, and for a brief, thrilling moment, they thought they were achieving fusion. Zeta, when it came online in 1957, produced what appeared to be thermonuclear neutrons, and the British government, in a moment of premature excitement, announced the results to the world in January 1958. It was front-page news. "Britain achieves fusion," the headlines essentially said. And then, within months, it became clear that the neutrons weren't coming from thermonuclear fusion at all. They were coming from the instabilities themselves. As the plasma kinked and writhed, ions were being accelerated to high energies and slamming into each other, or into the walls, producing neutrons through a non-thermal process. It wasn't fusion in the way that mattered. It wasn't a sustained, controlled thermonuclear reaction. It was just a violent, chaotic mess, producing a few neutrons as a side effect of its own instability. The Zeta embarrassment was a painful moment for the British program, and it taught the entire fusion community a lesson that would be repeated many times over the coming decades. Fusion plasma is extraordinarily difficult to control, and it will find ways to escape or disrupt itself that you haven't anticipated. The plasma, people sometimes say, has a mind of its own. It doesn't want to be confined. Every configuration you devise, it finds a way to wriggle out of. But something remarkable happened around this same time that would change the entire trajectory of fusion research. In 1958, the major powers agreed to declassify their fusion work. This happened partly through the Atoms for Peace initiative and partly through the Second United Nations International Conference on the Peaceful Uses of Atomic Energy, held in Geneva. And suddenly, after nearly a decade of working in isolation, the American, Soviet, and British fusion scientists could talk to each other. They could compare notes. They could see what the others had tried, what had worked, what had failed. And what they found, when they finally compared results, was both sobering and oddly reassuring. Sobering because everyone was struggling with the same fundamental problems: instabilities, energy losses, plasma that refused to stay hot and dense long enough to do anything useful. But reassuring because they realized they weren't alone in their difficulties. The problem wasn't that one group was incompetent. The problem was that plasma confinement was genuinely, fundamentally harder than anyone had imagined. The declassification also meant that the global fusion community could now collaborate, share ideas, and build on each other's work. And this is where the story starts to shift, because through the late 1950s and into the 1960s, the focus of research began to narrow. The pinch approach, while not abandoned entirely, fell out of favor as a primary path to fusion power. The stellarator showed promise, but was proving extraordinarily difficult to build with the precision required. Those twisted magnetic geometries demanded engineering tolerances that pushed the limits of what was possible at the time. And the tokamak, the Soviet design, was still relatively unknown in the West. its results published in Russian-language journals that many Western scientists didn't read closely. So through the early and mid-1960s, fusion research entered what you might call its adolescence, a period of growing up, of learning just how complicated the problem really was, of developing the theoretical tools and diagnostic techniques needed to understand what was actually happening inside these machines. Physicists were learning to measure plasma temperature, density, and confinement time with increasing precision, and what they found was discouraging. The plasmas in their machines were losing energy far faster than theory predicted. Heat was leaking out through mechanisms that weren't fully understood. Particles were escaping confinement much more quickly than they should have been. There was a growing sense that maybe fusion power wasn't 20 years away. Maybe it was much further than that. And then, in the mid-1960s, a team at the Kurchatov Institute in Moscow, led by a physicist named Lev Artsimovich, started reporting results from their latest tokamak that seemed almost too good to be true. They claimed plasma temperatures and confinement times that were dramatically better than anything anyone else was achieving, better by a factor of 10 or more. The Western fusion community was skeptical, deeply skeptical. Some thought the Soviet measurements were simply wrong, that their diagnostic techniques were flawed. After all, measuring the temperature of a plasma, a gas at 100 million degrees that you can't touch, can't insert a thermometer into, is incredibly difficult. And the Soviets were using indirect measurement methods that many Western physicists didn't fully trust. So in 1969, in one of the great moments of Cold War scientific diplomacy, a team of British physicists traveled to Moscow carrying something rather special, a newly developed diagnostic instrument based on laser light scattering, called Thomson scattering, which could measure plasma temperature directly and independently. The Soviets, to their credit, welcomed the British team and gave them access to their tokamak, the T3. And when the British pointed their laser at the Soviet plasma and analyzed the scattered light, they confirmed that the Soviets were right. The plasma in the T3 tokamak was genuinely reaching temperatures of around 10 million degrees Celsius, with confinement times that blew everything else out of the water. The British measurements matched the Soviet claims almost exactly, and just like that, the entire direction of fusion research pivoted. Think about what that moment meant. For over a decade, the Western fusion community had been pouring resources into stellarators, into pinch machines, into all sorts of clever magnetic configurations, and progress had been painfully slow. And here was this relatively simple Soviet design, a plain, round donut with a current running through the plasma itself to create the twisting magnetic field, outperforming everything else by an enormous margin. The reaction was swift and, honestly, a little dramatic. Within just a few years, fusion labs around the world essentially abandoned their existing approaches and converted to tokamaks. Princeton, which had been Lyman Spitzer's stellarator stronghold for nearly 2 decades, literally rebuilt their flagship machine into a tokamak. They called it the symmetric tokamak, and later the Princeton Large Torus. Oak Ridge did the same, the British did the same, the French, the Germans, the Japanese. Everyone pivoted to tokamaks. It was one of the most rapid and complete shifts in direction that any field of science has ever experienced. And here's the thing. It wasn't just that the tokamak worked better. It was that the tokamak worked better for reasons people could begin to understand. The key insight, the thing Sakharov and Tam had gotten right from the beginning, was that you needed the magnetic field lines to twist as they went around the torus. Remember, in a plain donut-shaped magnetic bottle, the field is stronger on the inside of the curve and weaker on the outside, and that imbalance causes particles to drift sideways and escape. The stellarator solved this by physically twisting the entire vacuum chamber into complicated shapes. The tokamak solved it much more elegantly by driving a massive electrical current through the plasma itself. That current, combined with the external magnetic field from the coils wrapped around the torus, created a helical, spiraling field that kept particles on closed orbits. No crazy figure-8 geometry needed, just a transformer coil in the center of the donut, inducing current in the plasma the same way the primary winding of a transformer induces current in the secondary. Beautifully simple. Now, the tokamak wasn't perfect. It had its own problems, and we'll get to those. But in the early 1970s, there was a genuine surge of optimism. The tokamak seemed to have cracked the confinement problem, at least partially, and the question shifted from, can we confine plasma at all, to, can we build a tokamak big enough and hot enough to actually produce net energy? Because that was always the goal, right? Not just to create fusion reactions. They'd been doing that in hydrogen bombs since 1952. But to create controlled, sustained fusion that produces more energy than you put in. And the physics suggested that if you could make a tokamak large enough, with a strong enough magnetic field, you could get there. This is where a concept called the Lawson criterion becomes really important, and it's worth spending a moment on, because it's one of those ideas that clarifies everything once you understand it. A British engineer named John Lawson had worked this out back in 1955, and it's elegant in its simplicity. Lawson asked a straightforward question. What conditions does a fusion plasma need to meet in order to produce net energy? And he boiled it down to 3 numbers: temperature, density, and confinement time. The temperature needs to be high enough for the nuclei to overcome their electromagnetic repulsion and fuse. For deuterium-tritium fuel, that's somewhere around 150 million degrees Celsius, about 10 times hotter than the center of the sun. The density needs to be high enough that nuclei actually collide with each other frequently. And the confinement time, the amount of time you can hold the plasma together at those conditions, needs to be long enough for enough fusion reactions to occur that the energy released exceeds the energy you spent heating and confining the plasma in the first place. Here's what's really clever about Lawson's analysis. He showed that what matters is the product of these quantities, density multiplied by confinement time multiplied by temperature. You can think of it like a 3-dimensional target. You need all 3 numbers to be high enough simultaneously. If your plasma is incredibly hot but too thin, you won't get enough collisions. If it's dense and hot, but you can only hold it together for a microsecond, not enough reactions will happen. You need the triple product to exceed a certain threshold, and that threshold is what the Lawson criterion defines. For deuterium-tritium fusion producing net energy, you need the triple product to reach roughly 3 times 10 to the 21. That's density in particles per cubic meter, times confinement time in seconds, times temperature in kilo-electron volts. Those units might not mean much to you lying there in the dark, and that's fine. The point is that it's a single number, a single target, and every fusion experiment in the world can be measured against it. How close are you to the Lawson criterion? That became the scoreboard. And in the early 1970s, tokamaks were climbing that scoreboard faster than anyone had expected. But climbing it and reaching the top are very different things. The triple product needed for net energy was still orders of magnitude beyond what any machine had achieved. So, the question became, how do you get there? And the answer, at least the answer that most of the fusion community settled on, was to build bigger. Bigger tokamaks with stronger magnets and more powerful heating systems. The physics scaling laws suggested that larger plasmas would naturally confine energy better. The ratio of surface area to volume improves as you scale up, so proportionally less heat leaks out through the edges. It's the same reason a large animal stays warmer than a small one. An elephant loses less body heat per kilogram than a mouse. So the 1970s and early 1980s became the era of the big tokamaks. And I mean big. The United States built the Tokamak Fusion Test Reactor, TFTR, at Princeton. It was enormous. The plasma chamber was about 2.4 meters in major radius. The whole machine weighed hundreds of tons, and it was designed to actually burn deuterium-tritium fuel for the first time in a magnetic confinement device. Europe, through a collaboration called Euratom, built the Joint European Torus, or JET, at Culham in England, even bigger than TFTR, with a major radius of about 3 meters. Japan built JT-60. The Soviet Union built T-15. It was an international arms race, except instead of weapons, the goal was to be the first to achieve something called break-even, the point where the fusion power output equals the heating power input. Now, these machines cost serious money. TFTR cost around $314 million. JET cost even more. And this is where fusion research collides with politics in a way that would shape the field for decades. Because here's the thing about fusion. It's always been expensive, and it's always been almost there. There's that old joke, fusion is 30 years away, and always will be. That joke started circulating in the 1970s, and it stung because there was truth in it. Every time physicists got closer to their goals, new problems emerged that required even bigger, more expensive machines to solve. And politicians, understandably, started getting impatient. But the physics was genuinely progressing. Let me tell you about one of the problems that kept showing up, because it's fascinating and it illustrates just how weird plasma can be. It's called anomalous transport, and it drove fusion physicists absolutely crazy for decades. Here's the issue. Classical physics, the straightforward application of electromagnetic theory and particle dynamics, predicts how fast energy should leak out of a confined plasma. You can calculate it. Particles collide with each other, and each collision nudges them slightly across the magnetic field lines, and over time, this causes a slow diffusion of energy from the hot core to the cooler edge. The math is well understood. The problem is that real plasmas lose energy much, much faster than classical theory predicts. Sometimes 10 times faster, sometimes 100 times faster. The energy just pours out of the plasma through some mechanism that the textbooks didn't account for. This is anomalous transport, and understanding it consumed an enormous amount of intellectual effort. What physicists eventually figured out is that plasma is not a smooth, well-behaved fluid. It's turbulent. Tiny instabilities, little ripples and eddies in the plasma, create microscopic electric fields that kick particles across field lines far more effectively than simple collisions do. Imagine you're trying to hold water in a bowl, and the water is perfectly still. It stays put just fine. But now imagine the water is churning and sloshing violently. It slops over the edges much faster. That's roughly what's happening in a tokamak plasma. The magnetic field is the bowl, and the plasma turbulence is the sloshing. The maddening thing was that this turbulence was incredibly difficult to predict or control. It depended on the details of the plasma profile, how temperature and density varied from the center to the edge, and it could change suddenly and unpredictably. You'd think you had a nicely confined plasma, and then some instability would kick in and the temperature would crash in milliseconds. These events had names: Sawtooth oscillations, edge-localized modes, disruptions. A disruption was the worst. That's when the plasma confinement fails catastrophically, and all the stored energy dumps into the walls of the machine in a fraction of a second. In a big tokamak, a disruption can release the energy equivalent of a small bomb. It doesn't cause a nuclear explosion. There's no possibility of that. But it can seriously damage the machine. The forces generated during a disruption from the sudden collapse of the plasma current can be enormous. Imagine millions of amperes of current suddenly finding a new path, inducing massive eddy currents in the metal structure. The machine can literally shake. Components can crack. TFTR experienced disruptions. JET experienced them. Every tokamak does. Learning to predict, avoid, and survive disruptions became one of the central engineering challenges of the whole program. And yet, despite all of this, the anomalous transport, the instabilities, the disruptions, the eye-watering costs, the big tokamaks of the 1980s and 1990s made remarkable progress. They were pushing the Lawson triple product higher and higher, approaching that magic threshold of break-even. JET, in particular, was about to do something that no one had ever done before in a controlled magnetic confinement device. Something that would prove the fundamental physics was sound, even as it revealed just how far the engineering still had to go. In November of 1991, the team at Cullum loaded their machine with a mixture of deuterium and tritium, real fusion fuel, the stuff that would actually produce the energy-releasing reactions you'd want in a power plant. And for the first time in a controlled magnetic confinement experiment, they got significant fusion power out. Not a lot, about 1.7 megawatts, and only for a couple of seconds. But think about what that meant. Real fusion reactions, real neutrons carrying real energy, born from the collision of deuterium and tritium nuclei inside a magnetically confined plasma. It wasn't a bomb. It wasn't a star. It was a machine, built by human hands, doing what the sun does, on purpose, in a building in the English countryside. Now, 1.7 megawatts might not sound like much, and honestly, it wasn't. The heating power going into the plasma was far more than what came out. This wasn't break-even. It wasn't even close, but it was proof of concept. It was the moment when fusion went from, we think this should work, to, we just watched it work. And the team at JET knew they were just getting started. That 1991 experiment was almost a preliminary run, a shakedown. The real push came a few years later in 1997, when JET ran a much more ambitious series of deuterium-tritium experiments. This time, they achieved 16.1 megawatts of fusion power. 16 megawatts. That's enough to power something like 10,000 homes, at least for the roughly 1 second it lasted. The ratio of fusion power out to heating power in what physicists call Q reached about 0.67. So for every watt they pumped in, they got back about 2/3 of a watt from fusion. Still not break even, still not Q equals 1, but remarkably close considering how far they'd come from those early days of plasma lasting microseconds. Here's the thing about JET's 1997 record, though. It stood for over 20 years. No one beat it. Not because people stopped trying, but because hardly anyone else was running deuterium-tritium experiments. And there's a very practical reason for that. Tritium is radioactive. It has a half-life of about 12.5 years, and when you use it in a fusion reactor, the neutrons produced by the DT reaction are extremely energetic. 14.1 million electron volts each. Those neutrons slam into the walls of the machine and make everything they touch radioactive through a process called neutron activation. After a DT campaign, Your reactor vessel becomes a radioactive environment. You can't just walk in with a wrench and fix things. You need remote handling equipment, shielding, decontamination procedures. The cost and complexity of running tritium experiments are enormous compared to running the same machine with just deuterium, which produces far fewer and less energetic neutrons. So most tokamaks, most of the time, ran with deuterium only. You can still study plasma physics, still measure confinement, still push temperatures higher. You just aren't producing the full energy fusion reactions. JET was one of the very few machines in the world designed from the start to handle tritium safely, with the containment systems and remote maintenance capabilities that required. TFTR at Princeton also ran DT experiments. Actually, TFTR did it first, in December 1993, achieving about 10.7 megawatts of fusion power. So Princeton beat JET to the punch by about 4 years, though JET ultimately achieved the higher power record. There's a friendly rivalry there, but both results were historic. And this is where the story gets complicated, because even as these machines were proving that fusion worked, the political and financial landscape was shifting under the scientists' feet. TFTR was shut down in 1997, the same year JET set its record, not because it had failed, but because the funding wasn't there to keep it running. The U.S. fusion budget had been declining since the mid-1980s. There was a moment in the mid-70s when fusion funding in America was actually on a trajectory that, if maintained, might have delivered a working fusion reactor by the early 2000s. The Department of Energy had laid out several scenarios. They literally published a chart showing that if you funded the program at a certain level, you'd get a demonstration plant by a certain date. The highest funding level was labeled something like maximum effective effort. The actual funding that materialized? It tracked below even the lowest scenario on the chart, the one labeled Fusion Never. That chart has become famous in the fusion community, a kind of bitter punchline. We chose the path where fusion never arrives, and then we mock fusion for never arriving. But let's not get too deep into the politics just yet. What matters for understanding the engineering is what these experiments taught us. And the biggest lesson from JET and TFTR and JT60, Japan's big tokamak, which achieved equivalent break-even conditions using deuterium-only plasmas and extrapolating what would have happened with tritium. The biggest lesson was about scaling. The physics worked, the reactions happened, the energy came out, but the machines weren't big enough to get to Q equals 1 or beyond, and the reasons came down to that stubborn problem of energy confinement time. Remember the Lawson criterion. You need the triple product of temperature, density, and confinement time to exceed a certain threshold. Temperature, they could do. The big tokamaks routinely achieved hundreds of millions of degrees, well above what you need for DT fusion. Density was manageable too, not stellar core density, but enough. The killer was confinement time. Energy leaked out of the plasma too fast, carried away by that anomalous transport we talked about, the turbulence that no one could fully suppress. And here's the scaling argument that drove the next generation. In a bigger machine, with a bigger plasma volume, the ratio of volume to surface area improves. Energy is generated throughout the volume, but lost mainly through the surface. Make the machine bigger, and you gain ground. The confinement time tends to increase with size. This isn't just hand-waving. There are empirical scaling laws, painstakingly assembled from data across dozens of tokamaks worldwide, that quantify exactly how confinement time depends on machine size, magnetic field strength, plasma current, and other parameters. The most famous of these is called the ITER98 scaling law, or more precisely IPB98 open parenthesis Y(2) close parenthesis, which is a mouthful, but it's basically a formula that says, if you build a tokamak this big, with this much current and this strong a magnetic field, you can expect a confinement time of roughly this many seconds. And when you plugged in the numbers for a machine significantly larger than jet, something with a plasma volume maybe 10 times bigger, the scaling laws predicted you could get to Q equals 10. Not just break even, but 10 times more fusion power out than heating power in. That's the kind of gain where you start to see a path to a real power plant. And that machine, of course, is ITER. Now, ITER is a story unto itself, and we'll get deeper into it. But let me tell you how it came to be, because the origin story is almost absurdly dramatic for what is essentially a physics experiment. It started with a conversation between Ronald Reagan and Mikhail Gorbachev. November 1985, Geneva, the same city where fusion had been declassified back in 1958. Reagan and Gorbachev were meeting for their first summit at the height of Cold War tensions, and they were looking for areas of cooperation, things they could agree on that would signal goodwill without requiring either side to give up anything strategically sensitive. And someone, the historical record suggests it was Evgeny Velikov, a Soviet physicist and advisor to Gorbachev, someone suggested fusion. It was perfect. Fusion research had been international since 1958. It had no weapons implications, at least not directly, and it was expensive enough that sharing the cost made sense for everyone. So Reagan and Gorbachev issued a joint statement calling for international cooperation on fusion energy, and from that handshake, ITER was born. The name ITER originally stood for International Thermonuclear Experimental Reactor, though later they sort of backed away from the acronym and leaned into the Latin meaning. ITER means the way in Latin, which is a nice touch. The project brought together the European Union, Japan, the Soviet Union, later Russia, and the United States. China, South Korea, and India joined later, 7 parties in all, representing over half the world's population. The design process took years. The original design, completed in the late 1990s, was enormous and enormously expensive, and the U.S. actually pulled out for a while in 1998, partly over cost concerns and partly because of domestic budget pressures. They came back in 2003. The design was revised, scaled down somewhat, though scaled down is relative when you're talking about a machine that would still be the largest tokamak ever built by a huge margin. Here's what ITER looks like in numbers. The plasma major radius, that's the distance from the center of the donut hole to the center of the plasma ring, is 6.2 meters. Jet's was about 3 meters. The plasma volume is 840 cubic meters, compared to Jet's roughly 80. The magnetic field on the plasma axis is 5.3 Tesla, generated by superconducting magnets made of niobium tin and niobium titanium, cooled to 4 degrees above absolute zero by liquid helium. The total weight of the machine is around 23,000 tons. It's being built in Cadarache, in the south of France, on a site that required leveling a small hill and pouring a seismic isolation platform because the region has earthquake risk. And the goal, the headline number, is Q equals 10. 500 megawatts of fusion power from 50 megawatts of heating input. Not for 1 second, but for pulses lasting 400 to 600 seconds, with the possibility of longer steady-state operation at lower Q. If ITER works as designed, it will be the first fusion device in history to produce more energy from fusion than is used to heat the plasma. The first time the Lawson criterion is decisively beaten in a burning plasma, a plasma where the energy from the fusion reactions themselves is the dominant source of heating, where the alpha particles born in DT reactions, those helium-4 nuclei carrying 3.5 million electron volts each, stay confined in the magnetic field and transfer their energy to the surrounding plasma, keeping it hot without external input. That's what a burning plasma means. It's self-heating, not self-sustaining. You still need the magnets, you still need the external systems, but the plasma itself is doing most of the thermal work. And that's a regime no one has ever operated in. JET's plasmas were heated primarily by external systems, neutral beam injection, radio frequency waves. The fusion reactions contributed some self-heating, but it was a minority of the total. In ITER, if everything goes right, the alpha particle heating will dominate, and no one knows exactly how a burning plasma will behave. The self-heating creates new feedback loops. If a region of plasma gets a little hotter, it fuses a little faster, which produces more alpha particles, which heat it more, which makes it fuse faster. That sounds like it could run away, but in practice, the increased pressure tends to expand the plasma and reduce density, which works against the reaction rate. There's a natural self-regulation. Probably. The models say so. But models have been wrong before about plasma behavior, and this is one of the things ITER is specifically designed to find out. The construction of ITER has been, to put it diplomatically, challenging. The project was formally established by international agreement in 2006. First plasma was originally targeted for 2016. Then it slipped to 2018. Then 2025. The most recent official schedule, as of the early 2020s, pushed first plasma to somewhere around 2035, with full deuterium-tritium operations not expected until the late 2030s at the earliest. The cost has ballooned from an initial estimate of around 5 billion euros to something north of 20 billion, depending on how you count and whose accounting you trust. The reasons for the delays are a fascinating case study in the difficulty of managing a massive international engineering project. Each of the 7 member parties manufactures specific components in their own countries and ships them to France for assembly. The central solenoid, the giant electromagnet at the heart of the machine that drives the plasma current, is built in the United States. The vacuum vessel sectors come from Europe and Korea. The toroidal field coils are split among Europe, Japan, Russia, and Korea. The diverter, the component at the bottom of the machine that handles the exhaust of heat and particles, involves contributions from multiple parties. Coordinating tolerances across components manufactured on different continents to fit together with millimeter precision in a machine the size of a building is an engineering challenge unlike almost anything else humans have attempted. Think about it this way. Imagine you're building a house, but the kitchen is being fabricated in Japan. The bathroom walls are coming from South Korea. The roof trusses are being assembled in the United States. The plumbing is manufactured in Russia, and the foundation was poured in France. And all of these pieces need to fit together not just well, but perfectly. We're talking tolerances measured in single-digit millimeters on components that weigh hundreds of tons. A single toroidal field coil, and there are 18 of them, stands about 17 meters tall and weighs around 360 tons. Getting one of those from a factory in Japan to a construction site in southern France is a logistics puzzle all by itself. They're too big for normal roads. Some of them had to travel by ship across the Pacific and through the Mediterranean, then up a specially widened road from the port at Fos-sur-Mer to the Cadarache site, a route that had to be modified, bridges reinforced, roundabouts redesigned, trees cleared, just to accommodate these enormous loads. And here's the thing about building something this precisely at this scale, with this many international partners. It's not just an engineering problem, it's a diplomatic one. Each member party has its own industrial base, its own manufacturing standards, its own quality control culture, and frankly, its own political pressures to ensure that its domestic industries get meaningful work from the project. That's part of the deal. Countries contribute in kind. They build components instead of just writing checks, because that's how you sustain political support for a multi-decade, multi-billion-dollar science project. You need legislators in Washington and parliamentarians in Tokyo and officials in Moscow to be able to point to factories in their own countries and say, look, this project is employing our people, advancing our technology. It's smart politics, but it makes the engineering coordination brutally difficult. There have been quality issues, components that arrived and didn't quite meet spec, welding defects discovered after fabrication, thermal shield panels that needed reworking. In 2022, the ITER organization disclosed that there were problems with the thermal shields and the vacuum vessel sectors. Specifically, certain welds and fabrication tolerances were not meeting the required standards, and repairs would be needed before assembly could proceed. This wasn't a minor hiccup. It contributed to yet another schedule revision. The leadership of the project has turned over multiple times, with different directors, bringing different management philosophies, trying to wrangle this sprawling multinational enterprise into something that can actually deliver a working machine. And it's worth pausing here to acknowledge something that often gets lost in the frustration about ITER's delays and cost overruns. What they're attempting to build is genuinely unprecedented. There is no instruction manual for assembling the world's largest tokamak. There's no previous version to learn from at this scale. Every single step, lifting a 1,000-ton vacuum vessel sector with centimeter accuracy, joining superconducting coils that must operate at 4 Kelvin, which is colder than outer space, integrating millions of individual parts from dozens of countries. Every step is being done for the first time. The delays are real, and they matter, because every year of delay is another year that fusion energy doesn't contribute to solving climate change. But the technical ambition is staggering, and a lot of the difficulty was, in some sense, predictable. Big international science projects almost always cost more and take longer than planned. The International Space Station did. The Large Hadron Collider did. ITER is following that same painful but familiar trajectory. So let's talk about what happens if ITER works. If it achieves its goal of Q equals 10, 500 megawatts of fusion power from 50 megawatts of heating input, sustained for hundreds of seconds, what does that actually prove? It proves that a burning plasma is physically achievable and controllable. It proves that the scaling laws were right, that the models held up, that alpha particle self-heating does what we think it does. That would be enormous. But, and this is important, ITER is not a power plant. It's not connected to the electrical grid. It doesn't generate electricity. All that fusion power, all 500 megawatts of it, gets absorbed by the walls of the machine and carried away by cooling water. It's an experiment, not a prototype reactor. The step from ITER to an actual fusion power plant is itself a massive engineering leap, and that's where the next generation of machines comes in. For decades, the conventional roadmap said that after ITER, you'd need another machine, a demonstration power plant, usually called demo, that would actually generate electricity from fusion and prove the technology works at a commercial scale. Various countries have been sketching designs for demo for years. Europe has its version. China has one. Korea has one. The general idea is a machine somewhat larger than ITER, or at least more optimized, that runs in steady state rather than in pulses, breeds its own tritium, and connects to a turbine and generator to produce electricity. Demo was always projected to come online sometime in the 2040s or 2050s, with commercial fusion power following in the 2060s or beyond. That timeline has led to the old joke that fusion is always 30 years away. And honestly, for most of the history of the field, that joke has been painfully accurate. But here's where the story takes a genuinely surprising turn, something that even people who've followed fusion for decades didn't fully see coming. Starting around the mid-2000s and accelerating dramatically into the 2020s, a wave of private fusion companies emerged, funded by venture capital and billionaire investors, claiming they could build fusion machines faster and cheaper than the giant government-funded projects. And unlike previous waves of private fusion enthusiasm, which tended to be fringe efforts with questionable physics, many of these new companies are led by serious scientists from top institutions using approaches grounded in real plasma physics and backed by genuinely significant amounts of money. The most prominent of these is probably Commonwealth Fusion Systems, or CFS, which spun out of MIT in 2018. And their story is fascinating because it's built on a single key technological bet, a bet about magnets. Remember how we talked about magnetic confinement, how the whole point of a tokamak is to use powerful magnetic fields to hold the plasma in place? Well, the strength of those magnets matters enormously. The stronger your magnetic field, the harder you squeeze the plasma, and the better you confine it. The fusion power output scales very steeply with magnetic field strength, roughly as the fourth power of the field. So, if you can double your magnetic field, you don't just get twice as much fusion power. You get something like 16 times as much. That's a game-changing relationship. ITER uses superconducting magnets made from an alloy called niobium tin, which is a well-established superconductor but has limitations on how strong a field it can produce. ITER's toroidal field is about 5.3 Tesla on axis. That's strong, much stronger than, say, an MRI machine, but it's not the limit of what modern superconductor technology can achieve. What CFS bet on was a newer class of superconducting material called high-temperature superconductors, specifically a material known as REBCO, rare earth barium copper oxide. Now, the name high-temperature superconductor is a bit misleading. These materials still need to be cooled to cryogenic temperatures, typically around 20 Kelvin, which is minus 253 Celsius. But that's dramatically warmer than the 4 Kelvin that conventional low-temperature superconductors like niobium tin require. And more importantly for fusion, REBCO can carry much larger currents and produce much stronger magnetic fields. In September 2021, CFS demonstrated a large-bore REBCO magnet that achieved a field of 20 Tesla. 20 Tesla. That's nearly 4 times the field strength of ITER's magnets. And because fusion power scales as roughly the fourth power of the field, that means, at least in principle, you could get ITER-level fusion performance from a machine that's dramatically smaller. Their planned device, called Spark, is designed to be roughly 1/40th the volume of ITER, but aims to achieve Q greater than 2. Possibly as high as Q equals 11. A machine the size of a large room, rather than the size of a building, potentially matching or exceeding ITER's fusion performance. That's the promise anyway. Now, you should be appropriately skeptical. plasma physics has a long history of promising more than it delivers, and there are real questions about whether the engineering challenges of a compact, high-field device are truly easier than those of a larger, lower-field machine like ITER. When you shrink the machine but keep the fusion power the same, you concentrate all that energy into a much smaller volume. The heat loads on the walls become more intense. The neutron damage to materials happens faster. The engineering margins get tighter. CFS and the MIT team behind SPARC are well aware of these challenges, and they argue that the advantages of compactness, faster construction, lower cost, more rapid iteration, outweigh the difficulties. SPARC is currently under construction in Devens, Massachusetts, with the goal of achieving first plasma around 2026 and deuterium-tritium operations sometime after that. But CFS is far from the only player. There's TAE Technologies in California, which has been around since 1998 and is pursuing a completely different approach, a field-reversed configuration that uses a beam of high-energy particles to stabilize the plasma. There's Tokamak Energy in the UK, which is also betting on high-temperature superconductors, but with a spherical tokamak design, a more compact cored apple shape rather than the traditional donut. There's General Fusion in Canada, which tried an audacious approach involving pistons that compress liquid metal around a plasma target, a kind of hybrid between magnetic and inertial confinement. There's Helion Energy in Washington State, which is doing something particularly unusual. They collide two plasma rings together at high speed and try to extract energy directly as electricity, without even using a steam turbine. And there's Zap Energy, also in Washington, pursuing a sheared flow Z-pinch, which is in some ways a modern descendant of those very earliest pinch experiments from the 1940s and 1950s, but with crucial stabilization tricks that the pioneers didn't have. As of the early 2020s, private fusion companies had collectively raised something on the order of $6 billion in investment. That's still small compared to ITER's budget, but it's an astonishing amount for a field that was, until recently, considered too speculative for private capital. The Fusion Industry Association, a trade group that didn't even exist until 2018, now has dozens of member companies. Something has shifted in how the world thinks about fusion, and a big part of that shift is the urgency of climate change. The old timeline, commercial fusion by 2060 or 2070, feels unacceptable when you're staring down the need to decarbonize the global energy system by mid-century. The private companies are explicitly pitching fusion as a climate solution, arguing that with enough funding and the right technology bets, they can compress the timeline dramatically. Whether they're right is one of the most consequential open questions in energy technology. And it depends not just on plasma physics, the confinement, the heating, the stability, but on a whole set of engineering challenges that don't get nearly as much attention as they deserve. Challenges that have been lurking in the background of the fusion story for decades, waiting for the moment when someone actually needs to solve them. And the biggest of these, the one that keeps fusion engineers up at night more than almost anything else, is the problem of materials. Specifically, what do you build the walls out of? What substance can you possibly put between a plasma that's running at 100 million degrees and the rest of your reactor and expect it to survive? Not for a few seconds, not for a few minutes, but for years of continuous operation in a commercial power plant. This is the problem that makes plasma physicists grateful they're plasma physicists and not materials scientists, because honestly, it's a nightmare. Let me paint the picture for you. In a fusion reactor burning deuterium and tritium, which is the fuel mix that every near-term reactor design is built around, About 80% of the energy released comes out not as heat in the plasma, but as neutrons. High-energy neutrons, each carrying 14.1 million electron volts of kinetic energy. That number matters. These aren't the relatively gentle neutrons you'd find in a fission reactor. Fission neutrons typically carry about 2 million electron volts. Fusion neutrons carry 7 times more energy per particle. And unlike charged particles, which the magnetic field can wrangle and steer and contain, neutrons have no electric charge. The magnetic field is completely invisible to them. They fly straight out of the plasma in every direction, slam into whatever solid material surrounds the reaction, and start doing damage at the atomic level. Here's what happens when a 14.1 mega-electron-volt neutron hits a metal wall. It collides with atoms in the crystal lattice of the metal, and because it's carrying so much energy, it can knock those atoms completely out of their positions. Each incoming neutron can displace not just one atom, but trigger a whole cascade. One collision leads to another, which leads to another, like a microscopic game of billiards where every ball is knocked loose. Over time, this creates enormous numbers of vacancies and displaced atoms in the metal's crystal structure. Materials scientists measure this in a unit called displacements per atom, or dPa. In a fusion power plant, the first wall, the surface directly facing the plasma, might experience something like 20 to 30 dPa per year. For comparison, the most demanding fission reactor components might see a few dPa per year, and even that causes significant degradation over a reactor's lifetime. So we're talking about a radiation environment that's qualitatively more punishing than anything we've ever built for. And it's not just the displacement damage. Those neutrons also trigger nuclear reactions inside the wall material itself. When a high-energy neutron is absorbed by an atom of, say, iron or chromium, it can transmute that atom into a different element entirely, often producing helium or hydrogen gas in the process. The helium atoms are particularly insidious. They're insoluble in metals. They don't dissolve into the crystal structure the way carbon might dissolve in iron. Instead, they cluster together into tiny bubbles, and those bubbles collect at grain boundaries, the natural interfaces between microscopic crystal grains in the metal. Over time, those helium bubbles cause the material to swell and become brittle. The metal literally puffs up and loses its ability to deform without cracking. This is called helium embrittlement, and it's one of the most feared degradation mechanisms in fusion materials science. You can't design around it with clever geometry. You can't fix it with better cooling. It's an intrinsic consequence of putting any solid material in the path of 14 MeV neutrons for long enough. So what do you use? What material can withstand this kind of abuse? This question has been studied intensively since at least the 1970s, and the honest answer is that no perfect material exists. But there are candidates, and the leading one for most reactor designs is a family of steels called reduced activation ferritic martensitic steels, often abbreviated RAFM. The most studied version is called Eurofer 97, developed in Europe specifically for fusion applications. The idea behind reduced activation steels is that you carefully control the alloy composition. You remove elements like molybdenum and niobium that would become highly radioactive under neutron bombardment and replace them with elements like tungsten and tantalum that produce less long-lived radioactivity. The goal isn't to eliminate activation entirely. That's impossible. But to ensure that after the reactor is decommissioned, the radioactive waste decays to safe levels within about 100 years, rather than the thousands of years you'd worry about with conventional reactor materials. That's a meaningful difference. It's the difference between waste you can plan to manage and waste that burdens civilizations you'll never meet. But even RAFM steels have limits. They start losing their mechanical strength above about 550 degrees Celsius, which constrains how hot you can run your coolant, which in turn limits the thermodynamic efficiency of your power plant. And they're still susceptible to radiation damage over time, meaning you'd need to replace major structural components periodically during the reactor's life. That's not a deal breaker, but it's a significant engineering and economic challenge. Imagine having to swap out the inner wall of a reactor vessel that's been made intensely radioactive by years of neutron bombardment. You can't send workers in. You'd need remote handling systems, essentially giant robotic arms operating in a highly radioactive environment with extreme precision. ITER is actually designed with remote handling in mind, and the systems are extraordinarily complex. Some of the maintenance operations planned for ITER involve robotic systems that weigh several tons, operating through narrow ports in the reactor vessel, manipulating components that must be positioned to within a fraction of a millimeter. It's like performing surgery with a crane inside a radioactive oven by remote control. Tungsten is another material that shows up constantly in fusion reactor designs, but for a different role. While steel might form the structural backbone, tungsten is the leading candidate for the plasma-facing surface, the very outermost layer that directly contacts the plasma edge. Tungsten is attractive because it has the highest melting point of any metal, about 3,420 degrees Celsius. It has low erosion rates under plasma bombardment, and it doesn't absorb much tritium, which matters for both fuel economy and safety. You don't want your wall material soaking up your expensive radioactive fuel like a sponge. But tungsten has its own problems. It's brittle at room temperature, which makes it difficult to manufacture and join to other components. And under neutron irradiation, it becomes even more brittle. There's also the issue of tungsten dust, tiny particles eroded from the surface by plasma interactions, which can accumulate inside the reactor vessel and pose both a safety hazard and a contamination problem. Now, here's something that doesn't get talked about enough in the popular press. We don't actually have a facility on Earth where we can test materials under the exact neutron conditions they'd face in a fusion power plant. Fission reactor neutrons have the wrong energy spectrum. Particle accelerator neutron sources can produce the right energies, but only in tiny volumes and at lower fluxes than a real fusion reactor would generate. There's been a long-discussed proposal for a facility called IFMIF, the International Fusion Materials Irradiation Facility, which would use two powerful particle accelerators to slam deuterons into a flowing curtain of liquid lithium, producing a neutron field that closely mimics what you'd get inside a fusion reactor. A smaller prototype, called IFMIF-DONES, is currently being planned for construction in Granada, Spain, and it would be the first facility capable of testing materials under truly fusion-relevant neutron conditions. But it hasn't been built yet, which means that right now, our understanding of how materials will behave inside a real fusion reactor involves a fair amount of extrapolation and modeling. We're reasonably confident in our predictions, but there's an unavoidable gap between what we've tested and what we'll actually encounter. And then there's the blanket, not a blanket you'd sleep under. Though honestly, thinking about blankets right now isn't a bad idea. But the fusion blanket, which is one of the most critical and least glamorous components of a fusion power plant. The blanket surrounds the plasma chamber, sitting just behind the first wall, and it has two essential jobs. First, it has to capture the kinetic energy of all those escaping neutrons and convert it into heat, which then gets carried away by a coolant, helium gas or liquid metal or pressurized water, depending on the design, and used to drive a turbine and generate electricity. Second, and this is really clever, the blanket has to breed tritium. Remember, tritium is one of the two fuels in a DT fusion reaction, and it's extraordinarily rare in nature. It's radioactive with a half-life of about 12 1/3 years, so it doesn't accumulate. You can't mine it. The world's entire stockpile of tritium is only about 25 kilograms, most of it produced as a byproduct in heavy water fission reactors, particularly the CANDU reactors in Canada. A commercial fusion power plant would burn through something like 55 kilograms of tritium per year, per gigawatt of output. The math simply doesn't work unless the reactor produces its own tritium. And the way you do that is by filling the blanket with lithium. When a neutron hits a lithium-6 atom, it triggers a reaction that produces tritium and helium. Lithium-7 can also produce tritium, though it requires a faster neutron and the reaction is less efficient. So the blanket is simultaneously your heat exchanger and your fuel factory. But here's the engineering challenge. You need to achieve what's called a tritium breeding ratio greater than 1, meaning for every tritium atom consumed in a fusion reaction, the blanket needs to produce at least one new tritium atom, and ideally a little more than one to account for losses and to build up an initial inventory for starting new reactors. Achieving a breeding ratio above 1 sounds straightforward in principle, but in practice, it's incredibly tight. Every neutron that escapes through a port, or gets absorbed by structural material instead of lithium, or leaks out through a gap in the blanket coverage, is a neutron that doesn't breed tritium. Reactor designers use neutron multipliers, typically beryllium or lead, mixed into the blanket to boost the neutron population through secondary reactions, giving themselves a little more margin. But the tolerances are thin. Some analyses suggest that achieving tritium self-sufficiency is one of the most uncertain aspects of the entire fusion energy enterprise. It's a problem that can only be fully validated by building and operating a real reactor with a real breeding blanket, which is part of what ITER's test blanket module program is designed to begin exploring. And this connects to something broader, something worth sitting with for a moment. The fusion challenge has always been described as a plasma physics problem. Can you confine the plasma, heat it enough, hold it long enough? And that's true. That is the central scientific question. But as we've moved closer to actually building reactors, the center of gravity has shifted. The plasma physics, while not fully solved, is increasingly well understood. The scaling laws point the way. The magnetic configurations work. What's less certain, what's arguably harder in some ways, is everything that surrounds the plasma. The materials that must endure the neutron bombardment. The blanket that must breed tritium reliably. The remote handling systems that must maintain components too radioactive for human contact. The tritium processing plant that must extract, purify, and re-inject tritium fuel on a continuous cycle while containing a substance that permeates through metals and is radiologically hazardous. The superconducting magnets that must operate flawlessly for decades. The heat exhaust system, called the divertor, that must handle power densities comparable to the surface of the sun, concentrated onto a target area roughly the size of a few parking spaces. The divertor, actually, is worth lingering on for a moment, because it illustrates just how extreme the engineering gets. In a tokamak, you can't let the plasma edge touch the wall everywhere uniformly. Instead, magnetic field lines at the plasma boundary are deliberately shaped to guide the hottest edge plasma down into a specially designed target region at the bottom of the vessel. That's the divertor. It's where the exhaust heat goes. In ITER, The diverter will need to handle steady-state heat fluxes of about 10 megawatts per square meter, with transient loads during plasma instabilities that can spike much higher. For reference, the heat flux at the throat of a rocket engine nozzle is in a similar range. The surface of the Sun, in terms of power radiated per unit area, is about 63 megawatts per square meter. So the diverter target isn't quite at solar surface levels, but it's in that neighborhood, and unlike the Sun, it has to be a solid engineered component that you can cool, inspect, and eventually replace. ITER's diverter uses tungsten monoblocks, small tungsten cubes with cooling channels drilled through them, bonded to copper alloy heat sinks, through which pressurized water flows. The manufacturing tolerances are extraordinary. Each bond between tungsten and copper alloy must be essentially perfect, because even a tiny void or delamination would create a hotspot that could lead to melting under the intense heat load. Thousands of these monoblocks are assembled into cassettes, and the full diverter consists of 54 cassettes arranged in a ring at the bottom of the vacuum vessel. And here's the thing. ITER's diverter is designed for experimental pulses, not continuous operation. A commercial reactor would need a diverter that lasts for years under similar or worse conditions. How you do that is still an open research question. Some groups are exploring liquid metal diverters, where instead of a solid surface, you have a continuously flowing film of liquid tin or lithium that absorbs the heat and carries it away, refreshing itself constantly so there's no solid surface to erode or damage. It's an elegant idea, but making it work reliably in a reactor environment with all the magnetic fields and plasma interactions is its own frontier of engineering. Because think about it. You've got this thin film of liquid metal, maybe a few millimeters thick, flowing across a surface, and it's sitting right there at the edge of a plasma that's 100 million degrees. Meanwhile, the entire machine is threaded with magnetic fields strong enough to levitate a train. Liquid metals are electrically conductive, so those magnetic fields interact with the flowing metal in complicated ways, creating forces that can slow the flow, redirect it, or make it unstable. It's a branch of physics called magnetohydrodynamics, which is one of those words that sounds like someone just kept gluing disciplines together until they ran out of room. But it's real, and it matters here, because if your liquid metal film stalls or bunches up or gets thrown off its surface by an electromagnetic force you didn't anticipate, suddenly you've got exposed solid material underneath, and you're right back to the erosion problem you were trying to avoid. Or worse, you've got droplets of liquid tin or lithium getting launched into the plasma edge, contaminating it, potentially triggering a disruption. So there are groups around the world working on this, at ENEA in Italy, at the Dutch Institute for Fundamental Energy Research, at several universities in the US and China, running small-scale experiments with flowing liquid metals in magnetic fields, trying to understand the flow patterns, the stability limits, the wetting behavior on different substrates, and they're making progress, genuinely. Lithium, in particular, has some interesting secondary benefits. When lithium atoms get into the plasma edge, they radiate energy very efficiently, which actually cools the edge plasma and spreads the heat load more evenly. It's like the liquid metal isn't just passively absorbing heat, it's actively helping manage the plasma boundary. Some experiments on the lithium tokamak experiment at Princeton and on EAST in China have shown measurably improved plasma performance when lithium conditioning is applied to the walls. So there's real physics backing up the idea. But going from a laboratory demonstration to a reliable, continuously operating liquid metal diverter in a power plant is a long road. And honestly, that's a sentence you could say about almost every subsystem in a fusion reactor. The physics works. The question is always whether the engineering can be made robust enough, reliable enough, and affordable enough to run for decades. And that word, affordable, let's sit with it for a moment, because it brings us to something that doesn't get discussed enough in the fusion conversation: the economics. You can build the most magnificent fusion reactor ever conceived, a machine that makes a star jealous. But if the electricity it produces costs 5 times as much as solar plus batteries, nobody's going to buy it. Fusion doesn't exist in a vacuum. Well, technically the plasma does, but the industry doesn't. It has to compete in an energy market that is changing fast. And the economics of fusion are genuinely uncertain right now, because nobody has built a commercial fusion power plant. Every cost estimate is, at best, an extrapolation from ITER scale experience and assumptions about future manufacturing. But let's walk through the logic. The fuel cost is essentially zero. Deuterium from seawater is practically unlimited and incredibly cheap to extract. Lithium for breeding tritium is abundant. It's the same lithium we use in batteries, and there's plenty of it in the Earth's crust and in seawater. So unlike fossil fuels, where the fuel itself is a major ongoing expense, fusion's operating fuel cost would be negligible. That's a real advantage. But the capital cost, the cost of building the machine, that's where things get challenging. ITER, as a one-of-a-kind experimental facility, is projected to cost somewhere north of $25 billion, depending on how you count. You wouldn't build a power plant that way, of course. A commercial reactor would be simpler in some respects. No experimental diagnostics, no test blanket module ports, more standardized components. But it would also need things ITER doesn't have, like a full tritium breeding blanket, a turbine hall, and the reliability to run for months without interruption. Various studies, from the European demo team, from the US fusion community, from private companies, have tried to estimate what a fusion power plant might cost. The numbers vary wildly, from maybe $4 to $8 billion for a gigawatt-scale plant in optimistic scenarios, to much higher in pessimistic ones. For context, a modern nuclear fission plant of similar capacity costs somewhere in the range of $6 to $12 billion in Western countries, though costs in South Korea and China have been significantly lower. A large natural gas combined cycle plant might cost $1 to $2 billion. Utility-scale solar farms are cheaper still per unit of capacity, though they need storage to provide firm power. Here's where the argument for fusion gets interesting, though. Fusion has no carbon emissions during operation. It produces no long-lived radioactive waste. The activated structural materials are a concern, but they decay to safe levels in 100 years or so, compared to tens of thousands of years for spent fission fuel. There's no risk of meltdown, because the plasma contains only a few grams of fuel at any time, and if anything goes wrong, the reaction simply stops. There's no chain reaction to run away. And fusion fuel is available to every country on Earth, so there are no geopolitical supply chain vulnerabilities like there are with oil, gas, or even uranium to some extent. These are powerful advantages. The question is whether they're powerful enough to justify the higher capital cost, especially in a world where renewables keep getting cheaper. And this is where the private fusion companies have introduced a genuinely new variable into the equation. Their whole thesis is that you don't need an ITER-sized machine to achieve net energy. If you can use high-temperature superconducting magnets to get much stronger fields in a smaller device, or if you can use a fundamentally different confinement approach that's more compact, then maybe your power plant costs $2 or $3 billion instead of 10. Maybe it fits on a site the size of a conventional power station instead of requiring a small campus. Commonwealth Fusion Systems has been explicit about this. Their ARC reactor concept, which would follow Spark, is designed to produce something like 200 to 500 megawatts of electricity from a machine that's dramatically smaller than ITER. If they can pull it off, and if the cost projections hold, it could be genuinely competitive. That's a lot of ifs. But the ifs are getting smaller. TAE Technologies has a different angle. Their approach, if it works with proton-boron fuel, would produce almost no neutrons, which means dramatically less material damage, simpler shielding, potentially cheaper maintenance. The trade-off is that proton-boron is much harder to ignite. You need temperatures around 1 billion degrees, roughly 10 times what deuterium-tritium requires. That's a staggering requirement. But TAE has been methodically working up through a series of machines. They're on their 5th generation now, called Copernicus. And they've been developing techniques for heating and confining plasma that are genuinely novel. Whether they can close the gap to 1 billion degrees is still an open question. But they're not just hand-waving. There's real physics and real hardware behind it. And then there's the regulatory question, which might sound boring, but is actually crucial. How do you regulate a fusion power plant? It's not a fission reactor. It doesn't have the same risks, doesn't produce the same waste, doesn't need the same kind of emergency planning zones. If regulators treat fusion the same as fission, the licensing process could take a decade and add billions in compliance costs, which would be economically devastating. But if fusion gets its own regulatory framework, one that's proportionate to its actual risks, the path to commercialization gets much smoother. The UK's Health and Safety Executive made a significant decision in 2021, ruling that fusion facilities in Britain would be regulated under conventional health and safety law rather than under nuclear fission regulations. That was a big deal. It sent a signal that at least one major government was willing to treat fusion differently. The U.S. Nuclear Regulatory Commission has been working on a similar framework, and in 2023 began developing fusion-specific regulations. These bureaucratic details might not sound exciting, but they could determine whether fusion power plants actually get built in the 2030s and 2040s, or whether they get stuck in regulatory limbo for decades. So where does all of this leave us? You've got ITER under construction in southern France, the largest and most complex scientific instrument ever attempted, designed to prove that sustained fusion energy gain is possible at scale. You've got demo on the drawing boards in Europe, China, South Korea, and potentially other countries, aiming to be the first fusion device that actually puts electricity on the grid, sometime in the 2040s or 2050s. And you've got a fleet of private companies, funded by billions in venture capital, racing to beat that timeline with smaller, cheaper, more innovative machines. Some of them will fail. Maybe most of them will fail. But the sheer diversity of approaches being pursued right now is unlike anything the fusion community has ever seen. And here's something worth thinking about as you lie there, letting all of this settle. The history of fusion research has been shaped, more than almost any other field, by the tension between physics and engineering. For decades, the dominant challenge was physics. Could you heat a plasma hot enough, confine it long enough, achieve the conditions for net energy? And the answer, as of JET's deuterium-tritium experiments and the scaling laws that point to ITER, is almost certainly yes. The physics works. We know how to make a burning plasma. The center of gravity has shifted. The hardest problems now are the ones we've been talking about. Materials that can survive a neutron bombardment for years, divertors that can exhale the heat of a small star, tritium breeding systems that can close the fuel cycle, superconducting magnets that can operate reliably for decades, and an economic model that makes the whole thing worth building. These are engineering problems, hard ones. Maybe some of the hardest engineering problems humanity has ever faced. But here's the thing. Humanity has a pretty good track record with hard engineering problems, once the physics is settled. Think about that for a second. The physics of powered flight was understood in broad strokes by the late 1800s. Lift, drag, thrust, the basic aerodynamics, people had a reasonable grasp. But turning that understanding into a machine that could actually carry a person through the air, reliably, safely, repeatedly, that took years of painstaking engineering. The Wright brothers didn't discover a new law of physics in December 1903 at Kitty Hawk. They solved an engineering problem, specifically, the problem of control. They figured out wing warping. They built a lightweight engine with enough power-to-weight ratio. They designed a propeller that was essentially a rotating wing. And even after they flew, it took another decade before airplanes were reliable enough to be useful, and another few decades before commercial aviation became routine. The physics didn't change. The engineering caught up. Or think about semiconductors. The transistor was invented at Bell Labs in 1947. The physics of semiconduction, the band gap, doping, electron, and hole carriers, was understood well enough to make that first device. But the journey from that first point contact transistor to the chip in your phone, with billions of transistors etched at scales of a few nanometers, that's 60+ years of relentless engineering. Lithography, chemical vapor deposition, ion implantation, extreme ultraviolet light sources, clean rooms where the air has fewer particles per cubic meter than outer space. None of that required new physics. It required engineering so precise, so creative, so persistent that it reshaped civilization. Fusion is at a similar inflection point. The plasma physics is not fully solved. There are still instabilities to manage, turbulence to model, edge physics to refine. But the fundamental question of whether you can create conditions for net energy from fusion on Earth has been answered. You can. JET proved it in 1997, and again in the record-breaking experiments of 2021 and 2022. The scaling laws derived from decades of tokamak experiments around the world predict, with reasonable confidence, that a machine the size of ITER will produce 10 times more fusion power than the heating power put into the plasma. Q equals 10. That's the target. And the physics community is broadly confident it will work. So the question isn't really, can fusion work, anymore. It's, can we build it in a way that's practical, durable, and affordable? And that's a different kind of question. It's the kind of question that engineers, given enough time and resources and motivation, tend to answer. Now, let's talk about what the next few years actually look like, because the timeline is getting concrete in a way it never has before. ITER is scheduled to achieve first plasma. Well, the timeline has shifted several times, and as of the early 2020s, the target for first plasma was pushed to around 2025. Then further delays pushed initial operations toward the late 2020s, with full deuterium-tritium experiments not expected until the 2030s. These delays are frustrating, but they're not unusual for a project of this complexity. The James Webb Space Telescope was decades late and billions over budget, and it's now producing the most extraordinary astronomical data humanity has ever seen. Sometimes the hardest projects just take longer than anyone wants. But while ITER inches forward, the private sector is moving fast. Commonwealth Fusion Systems, CFS, the MIT spin-off we talked about, broke ground on their Spark tokamak in Devens, Massachusetts. Spark is designed to be compact, about the size of a large room compared to ITER's cathedral-scale dimensions, and it aims to achieve Q greater than 2 net energy gain, using those high-temperature superconducting REBCO magnets that can generate fields of 20 Tesla or more. If Spark works as designed, it would be the first privately built fusion device to achieve net energy gain, and CFS plans to follow it with ARC, a commercial pilot plant producing somewhere in the range of 200 to 500 megawatts of electricity. Their stated goal is to have ARC operating in the early 2030s. That's ambitious, very ambitious, but they've already demonstrated the magnet technology, which was the single biggest technical risk in their plan. Then there's Helion Energy, based in Everett, Washington. Helion's approach is different from almost everyone else's. They use a field-reversed configuration, a compact self-contained plasma structure, and they collide two of these plasma structures together at high speed, compressing the merged plasma to fusion conditions. What's really unusual about Helion is their plan to extract energy directly from the fusion reaction as electricity, using the expanding plasma to drive a magnetic flux change that induces current. It's essentially a pulsed system, firing about once per second, and they claim this direct energy conversion could be far more efficient than the traditional approach of using fusion heat to boil water and spin a turbine. Helion's fifth machine, which they call Polaris, is designed to demonstrate net electricity production, and they've already signed a power purchase agreement with Microsoft, committing to deliver fusion electricity by 2028. Whether they hit that date is anyone's guess, but the fact that a major corporation is willing to sign a contract for fusion power tells you something about how the perception of this technology has shifted. TAE Technologies, the company pursuing proton-boron fusion, the one that needs temperatures around 1 billion degrees, is working on their 6th-generation machine, Copernicus, which they aim to have operational in the mid to late 2020s. Proton-boron fusion is harder than deuterium-tritium in terms of the temperatures required, but it has that extraordinary advantage of producing almost no neutrons. If TAE can make it work, you'd have a fusion reactor that doesn't damage its own walls, doesn't need tritium breeding blankets, doesn't generate significant radioactive waste. It's the cleanest possible version of fusion. The physics is daunting, but TAE has been working on this for over 20 years, and their sustained focus on a single, unconventional approach is either visionary or quixotic. Time will tell. And there are others. Tokamak Energy in the UK, building compact spherical tokamaks with high-temperature superconducting magnets, aiming for a pilot plant in the 2030s. General Fusion in Canada, still pursuing their magnetized target approach. Zap Energy, working on sheared flow stabilized Z-pinch plasmas without any magnets at all. First Light Fusion in Oxford, using projectile-driven inertial confinement, essentially firing a projectile at a target to create fusion conditions, like a tiny, controlled version of what happens in a star's core during a supernova shock. They've already demonstrated fusion neutrons with their approach. The landscape is rich, it's diverse, and it's moving. But let's be honest about what we don't know yet, because intellectual honesty is part of what makes this story so compelling. We don't know if any of these private companies will achieve their stated timelines. History suggests most will face delays. We don't know if compact fusion devices can operate reliably for the tens of thousands of hours needed for a commercial power plant. Running a fusion plasma for a few seconds, or even a few minutes, is fundamentally different from running one continuously for months or years. We don't know if tritium breeding blankets will work at scale, and for any deuterium-tritium approach, this is a make-or-break question. We don't know if the material solutions for neutron damage will hold up over the lifetime of a reactor, because we haven't had a neutron source intense enough to test them properly. And we don't know what fusion electricity will actually cost, because no one has ever sold a kilowatt-hour of fusion-generated electricity to anyone. These are real uncertainties. They're not reasons for pessimism, but they're reasons for humility. Fusion has been 30 years away for so long that the phrase has become a joke, and that joke exists because the field has repeatedly underestimated the difficulty of the engineering challenges. But the joke also obscures something important. The field has made enormous, measurable, undeniable progress. The fusion triple product, that combination of temperature, density, and confinement time that determines how close you are to net energy, has increased by a factor of more than 10,000 since the first tokamak experiments in the 1960s. That's a rate of improvement comparable to Moore's law in semiconductors. The difference is that fusion's improvement curve hasn't translated into a commercial product yet, because the threshold for usefulness in fusion is absolute. You either achieve net energy or you don't, and everything below that threshold is, from a practical standpoint, zero. But we're close to that threshold now, closer than we've ever been. And once you cross it, once you demonstrate sustained, reliable net energy from fusion, the engineering optimization that follows will be rapid, because that's what engineers do. They optimize, they iterate, they make things cheaper, smaller, more reliable. The first commercial airplane cost a fortune and carried one person. Within decades, airplanes were carrying hundreds of people across oceans for the price of a nice dinner. So, here's how I like to think about it. And maybe this is a good thought to hold as you drift off. Fusion power is the energy source that the universe itself runs on. Every star in the night sky, every point of light you've ever seen when you looked up on a clear evening, is a fusion reactor. The warmth on your face on a summer afternoon is energy that was released by fusion reactions in the core of the sun about 8 minutes ago. Well, technically, the photons took hundreds of thousands of years to random walk their way out from the core to the surface. But the energy traveled from the sun to your skin in 8 minutes. That energy started as hydrogen, the simplest element, the most abundant substance in the universe, and it was transformed into helium, into light, into warmth, into life, really, because without that fusion energy, Earth would be a frozen rock in the void. And what fusion researchers are trying to do, what they've been trying to do for 70 years, through all the setbacks and false starts and funding cuts and political complications, is bring a tiny piece of that stellar process down to Earth, to create a small controlled star in a bottle and use its energy to power our cities, desalinate our water, manufacture our goods, and do it all without carbon emissions, without long-lived radioactive waste, without the risk of meltdown, using fuel that's available to every nation on the planet for millions of years. It's an audacious goal, maybe the most audacious engineering goal in human history. And the fact that we haven't achieved it yet doesn't mean we won't. It means it's hard. Really, genuinely, profoundly hard. The kind of hard that requires the best materials scientists, the best plasma physicists, the best magnet engineers, the best computational modelers, the best project managers, the best welders, yes, welders, because someone has to join those vacuum vessel sectors with millimeter precision, and that's as essential as any equation. The story of fusion is a story about patience, about people who dedicated entire careers to a technology they knew they might never see completed, about governments that funded research for decades without a guaranteed return, about young engineers right now, today, walking into labs and startups and construction sites, choosing to work on this problem because they believe it matters. And it does matter. If fusion works, when fusion works, it changes the energy equation for our entire species. It doesn't solve every problem. You still need grids, transmission lines, political will, equitable distribution. But it removes the deepest constraint, the one that has shaped civilization since the first fire was lit, the scarcity of clean, dense, abundant energy. And you know, there's something quietly beautiful about the fact that the fuel for all of this is hydrogen, the lightest element, the first element, the element that formed in the first few minutes after the Big Bang, before there were stars, before there were planets, before there was anything at all. Hydrogen has been fusing in stellar cores for 13 billion years, building up the periodic table, element by element, forging the carbon in your bones and the oxygen in your lungs and the iron in your blood. And now, here on this small planet, a species made of those very elements is trying to learn the trick for itself, trying to close the loop, trying to do what the stars do. It's a good story, maybe the best one we've got. And wherever it goes from here, whether it's ITER that crosses the threshold first, or spark, or some machine we haven't even imagined yet, the story will keep being told. By engineers in labs, by welders in reactor halls, by physicists staring at plasma diagnostics at 3 a.m, by people like you who are curious enough to want to understand how it all works, even if you're hearing about it while you're half asleep. And that's okay. That's more than okay. Let it settle. Let the details blur if they want to. The big picture is simple, and it's worth holding on to. We figured out how stars work, and now we're learning to build one. It's taking longer than anyone hoped, but we're getting there. Slowly, carefully, one breakthrough at a time. And the light, when it comes, will have been worth the wait.